Imagine this. You're heading to a high-level discussion on artificial intelligence. We're at the epicenter of digital discovery, Google's world headquarters, the Googleplex in Mountain View, California.
Okay.
You, a prominent visitor, somehow managed to get completely lost inside the very building dedicated to Google Maps.
Oh, wow. Yeah, that's something.
That's irony squared, as our source materials author Melanie Mitchell experienced firsthand back in May 2014. It's a perfect illustration, really, of a core tension in AI. Brilliant and world-changing in some areas, yet, surprisingly, almost comically, inept in others.
Absolutely. It captures that contrast perfectly.
Let's dig into this further. Today, we're taking a deep dive into the fascinating, often perplexing world of artificial intelligence.
Sounds great.
We're drawing extensively from Melanie Mitchell's insightful work, which really explores what computers can actually do, what we can realistically expect, and the profound questions AI raises about our own human intelligence.
Yeah, it's essential stuff if you want to get beyond the headlines.
Definitely. It's an essential journey to understand the true state of AI.
And what truly stands out about this topic, is the rapid fluctuation in the public narrative around AI.
Oh, absolutely. Whiplash sometime.
Exactly. Swinging wildly between immense optimism and profound skepticism. This deep dive will offer you, hopefully, a clear perspective on why there's such a wide spectrum of views from AI will solve everything to, it's summoning the demon.
Right, the whole gamut.
This constant oscillation between awe and apprehension is fundamental to grasping AI today, helping us move beyond the hype and into the nuanced reality.
And for you, our listener, our mission today is to offer a shortcut to being genuinely well-informed. We'll journey through AI's historical context, marvel at today's dazzling breakthroughs, uncover its often overlooked limitations, and wrestle with the ethical dilemmas it presents.
Yeah, cover the whole landscape.
By the end, you'll have a much clearer sense of AI's genuine accomplishments, its many unsolved problems, and its deep relevance to your life. Okay, let's transport ourselves back to that Googleplex meeting in 2014. Melanie Mitchell was there, observing the significant machine intelligence efforts led by Blaise Aguirre-Arcus.
Right, a big name.
Google, initially founded in 1998 as simply a web search portal, had rapidly evolved into what Mitchell aptly describes as an applied AI company.
Yeah, it wasn't just search anymore, not by a long shot.
AI had become the invisible glue holding together virtually all of its products, from Gmail and Google Translate to YouTube and Android.
It's everywhere in their ecosystem.
This wasn't just about finding information anymore. It was about seamlessly embedding AI into our daily digital lives.
And putting this into broader context, Google's overarching ambition for AI has always been incredibly expansive, really ambitious.
How so?
Well, the original mission statement for its DeepMind group, for example, wasn't just about creating useful applications. It was, rather audaciously, solve intelligence and use it to solve everything else.
Wow. Okay, that's a big goal.
Huge. It reveals a foundational quest to not just mimic, but truly understand and replicate intelligence itself. A vision that extends far beyond, just better photo tagging or translation.
And their commitment to this grand vision was evident in their recruitment strategy too, wasn't it?
Definitely. Google had brought in the often controversial futurist Ray Kurzweil.
Ah, yes.
Kurzweil.
A prominent proponent of the AI singularity, that theoretical near-future point where non-biological intelligence surpasses human intelligence.
Right. The point of no return, supposedly.
And Kurzweil's role was quite literally to help realize this vision. So imagine this. A technology giant pouring immense resources and some of the world's brightest minds into solving intelligence itself.
Quite a picture. Which brings us to a really fascinating point. Given Google's fervent pursuit of AI and its embrace of ambitious figures like Kurzweil, what was the general atmosphere like in that meeting room, especially for a seasoned AI researcher like Melanie Mitchell?
Well, the true focal point of that gathering was Douglas Hofstadter.
Exactly. A legendary figure in AI, celebrated author of Gödel, Escher, Bach, and Eternal Golden Braid, famously known as GE.
GE. Such an iconic book.
It really isn't just a book, it's a cultural touchstone. Written in the 1970s, this Pulitzer Prize-winning work explored complex ideas about how intelligence, consciousness, and self-awareness might emerge from biological systems and how computers might one day achieve them. It captivated countless young minds, including Melanie Mitchell, inspiring her to pursue AI research.
Yeah, I read she basically changed her whole career path after reading it.
Pretty much. In the early 1980s, after completing her math degree, she devoured GE and was so deeply inspired that she pursued a PhD with Hofstadter at Indiana University, despite having no prior computer science courses.
Wow, that's dedication.
It highlights the profound, almost philosophical allure AI had for many of its early pioneers.
And Hofstadter's personal journey in AI really reflects a broader evolution in the field itself, doesn't it?
It absolutely does. In the 1970s, he viewed AI as an exciting prospect, a profound intellectual adventure.
Full of optimism.
Totally. He firmly believed that AI was possible in principle, directly challenging skeptics like John Searle and Hubert Dreyfus, who argued it was fundamentally impossible.
Right, the philosophical debates were fierce back then.
And at that time, he estimated human-level AI was perhaps 100 Nobel Prizes away, with no danger on the horizon.
No danger on the horizon. That's an astonishing contrast to where he ended up.
Exactly. A critical turning point for Hofstadter's perspective came in the mid-1990s, catalyzed by something that might seem, well, almost innocuous: David Cope's experiments in musical intelligence, or EMI.
EMI, the music composing program.
That's the one. This program was designed to compose new musical pieces in the distinct styles of classical composers, like Bach and Chopin, by meticulously analyzing their existing works and applying complex rules.
And Hofstadter's reaction to EMI was anything but academic or mild. He apparently described it quite vividly in that Google meeting.
He did. He expressed a visceral emotional response. He said, "I was terrified by EMI. Terrified, I hated it, and was extremely threatened by it.
Terrified. Hated it.
It was threatening to destroy what I most cherished about humanity. I think EMI was the most quintessential example of the fears that I have about artificial intelligence."
That's an incredibly powerful statement, especially coming from someone who once championed AI's theoretical possibilities. What was it about that music, specifically, that could evoke such a profound response?
It's a crucial question, isn't it? What is it about a program that composes music that could so deeply unsettle someone who believed in the theoretical possibility of AI?
Yeah.
It really speaks to our core definitions of creativity and human uniqueness, forcing us to confront our assumptions about what true intelligence genuinely entails. And Hofstadter also articulated deep ambivalence about Google's broader AI ambitions, from self-driving cars to their own forays into music composition, and their embrace of Kurzweil's singularity vision.
Right, the whole grand project.
While he strongly doubted the singularity's premise, he conceded that Kurzweil's predictions still disturbed him, leaving him with a lingering fear that, will be completely caught off guard.
And Melanie Mitchell herself. How did she process all this?
Well, she left that meeting scratching her head in confusion. She had previously dismissed Kurzweil's books as largely ridiculous and firmly believed human-level AI was centuries away.
Okay, so she was a skeptic on that front.
Very much so. But these candid discussions with respected colleagues compelled her to critically re-examine her own assumptions, prompting her to ask if she had perhaps underestimated the power and promise of current-day AI.
It's a question I imagine many of you listening might also be asking yourselves. Have we underestimated it?
That's the central question, really.
So what does this initial journey tell us? Hofstadter's remarkable shift from an optimistic AI pioneer to someone literally terrified by a music-composing algorithm sets a compelling stage for our entire deep dive.
It really does.
It challenges you to question your own assumptions about AI's true capabilities and its profound implications for humanity.
It's not just about the technology.
Exactly. It's not just about what machines can do, but what their capabilities mean for our perception of ourselves, our creativity, and our unique place in the world.
Okay, let's rewind a bit. The field of AI formally began with a small yet profoundly impactful workshop at Dartmouth College in 1956.
The birthplace, essentially.
It was here that John McCarthy coined the term artificial intelligence, specifically to differentiate this burgeoning field from cybernetics. This moment marked the very genesis of AI as we understand it today.
And what's truly striking about that foundational moment is the sheer audacity of the early promises.
Oh, yeah.
Keep in mind, the computers of 1956 were about 1,000,000 times slower than the smartphones many of us carry today.
Right. Incredibly basic by today's standards.
Yet McCarthy and other pioneers like Marvin Minsky, Alan Newell, and Herbert Simon were incredibly optimistic, unbelievably optimistic.
Optimistic.
McCarthy boldly aimed for a fully intelligent machine in a decade.
Wow. A decade.
Herbert Simon predicted machines doing any work that a man can do within 20 years, and Minsky, similarly, forecasted that AI problems would be substantially solved within a single generation.
These were truly grand claims for such a nascent field. Almost naive looking back.
Well, fueled by excitement, I suppose.
Indeed. From its very inception, AI was fueled by these incredibly audacious predictions. Just imagine that level of excitement and belief in 1956 when computers were still largely unexplored territory.
A real sense of possibility.
But, as you might already anticipate, things didn't quite unfold according to that ambitious plan. Those early predictions, didn't quite pan out on their aggressive timelines.
No, reality intervened, as it tends to do.
One of the immediate and persistent challenges from the outset was simply defining intelligence itself. Voltaire's old adage, define your terms, rings especially true here.
It really does. Marvin Minsky famously called terms like intelligence, thinking, and consciousness suitcase words because, as he put it, they're packed with a jumble of different meanings.
Suitcase words, I like that. Very descriptive.
Yeah. This inherent ambiguity has profoundly shaped the entire trajectory of the field.
So how do they try to tackle it?
Well, in attempting to tackle this elusive concept, the field largely pursued two distinct philosophical and practical paths.
Okay.
One was more scientific, essentially trying to investigate and replicate natural or biological intelligence by embedding it within computer systems.
Kind of like reverse engineering the brain.
Sort of, yeah. The other was distinctly more practical, focusing simply on creating programs that could perform specific tasks as well as, or even better than, humans, without getting bogged down in whether those machines thought like us.
Just make it work.
Exactly. And interestingly, funding often became a decisive factor, steering researchers down one path or the other. Practical applications often got the money.
Makes sense. So the first path was known as symbolic AI. What did that involve?
This approach represented knowledge using symbols that were, in theory, understandable to humans, things like words or phrases, and then applied explicit rules for combining and processing them.
Okay, like logic rules.
Precisely. A classic example was the General Problem Solver, or GPS, an early program that could solve logic puzzles like missionaries and cannibals.
I remember that puzzle.
Yeah. The crucial point here is that the computer itself had no actual knowledge of the meaning of these symbols. Their meaning was purely derived from their interrelations and the operations performed upon them within the system. It was all syntax, no semantics.
Got it. Processing symbols without understanding them.
And this symbolic approach was dominant for the first 3 decades of AI research. We saw this manifest in expert systems like IMICIN, designed to assist with medical diagnoses.
Like those rule-based systems.
Yeah. In these systems, human experts would painstakingly distill their knowledge into explicit rules and encode them for the computer. The prevailing belief was that intelligence could be fully captured by a sufficiently complex system of symbol processing rules without needing to directly mimic the brain's intricate biological structure.
Okay, so that's symbolic AI. What was the alternative?
The alternative was subsymbolic AI. This approach took its direct inspiration from neuroscience, aiming to capture those unconscious thought processes that enable us to recognize faces or understand spoken words without explicitly thinking about the rules.
More brain-inspired then.
Exactly. These programs didn't rely on human understandable rules, but rather on complex stacks of equations operating on numbers designed to learn from data.
Learning from data. That sounds more familiar now.
Right. A key early example was Frank Rosenblatt's perceptron, which proposed networks of units that could act, for instance, as an 8 detector for handwritten digits, learning through numerical inputs and outputs.
The perceptron, a precursor to modern neural nets.
Absolutely. And what's truly fascinating is this early divergence, almost a philosophical split at the very heart of AI.
2 very different bets on how to achieve intelligence.
Exactly. Do you attempt to model human-like reasoning with clear, explicit rules, or do you build something that learns and works effectively from data, even if we don't fully comprehend how it thinks, or if it even thinks at all?
A fundamental debate.
And it profoundly shaped the field for decades, influencing research directions and theoretical perspectives.
But despite its early promise, subsymbolic AI faced a significant setback, didn't it?
It did. In 1969, Marvin Minsky and Seymour Papert published their influential book, Perceptrons.
Ah, yes, this was a big deal.
Huge. In it, they mathematically demonstrated the inherent limitations of simple perceptrons, arguing they couldn't solve more complex problems. And crucially, they also speculated on the sterility of multi-layer neural networks, essentially casting doubt on their future potential.
So they basically killed off that line of research for a while.
Pretty much. Their critique had a pronounced chilling effect across the field, leading to a sharp decrease in funding for neural network research throughout the 1970s.
Wow.
Simultaneously, by the mid-1970s, many of the grand breakthroughs in general AI, such as genuinely understanding speech or language that had been promised by symbolic AI proponents, simply hadn't materialized.
The grand promises weren't being kept.
No. And negative government reports in both the UK and US resulted in drastic cuts to basic AI research funding, effectively ushering in the first AI winter.
The AI winter, a famous term in the field.
This pattern became a recurring theme in AI's history, a vibrant AI spring characterized by optimism, hype, and robust funding, inevitably followed by an AI winter marked by unfulfilled promises, funding drying up, and a general slowdown in research.
It sounds cyclical.
Very much so. Melanie Mitchell herself recalls being advised to avoid using the term artificial intelligence on job applications in 1990 because of its tarnished image.
That really underscores how volatile the field has been.
Absolutely. Yet, even during that chilling effect, a small, dedicated group of neural network researchers quietly persevered.
Okay, so the flame didn't completely die out.
No. By the late 1970s and early 1980s, they developed a crucial breakthrough: backpropagation.
Backpropagation, the algorithm that changed everything for neural nets.
Exactly. This was a general learning algorithm that finally made it feasible to effectively train multi-layer neural networks. Essentially, it allowed these complex networks to learn effectively from their mistakes, adjusting their internal connections, their weights, to get better and better at a task.
So it provided a way to actually train those more complex networks Minsky and Papert are skeptical about.
Precisely. This backpropagation algorithm was a game changer, making it possible to train networks for tasks that were previously too difficult for simple perceptrons, like recognizing handwritten digits.
And this led to a revival.
Yes, it ignited a connectionist revival in the 1980s, championed by researchers like David Rumelhart and James McClelland. Their seminal 1986 treatise, Parallel Distributed Processing, powerfully argued that the brain's computational architecture was much better suited for natural information processing tasks, such as perceiving objects or understanding language, than the rule-based symbolic systems.
So a comeback for the brain-inspired approach.
Definitely. And in a twist of irony, at roughly the same time, the limitations of symbolic AI's expert systems were becoming painfully apparent.
The brittleness problem.
Exactly. By the mid-1980s, these systems were proving to be brittle, prone to errors, and unable to generalize beyond their narrowly defined domains.
Why was that?
It was largely because human experts unconsciously relied on vast amounts of subconscious knowledge or common sense that simply couldn't be easily coded into explicit rules.
You can't write rules for everything you know without knowing you know it.
Precisely. This shortcoming then led to another AI winter, this time for symbolic AI. It highlights how both foundational approaches, in their own ways, face significant hurdles in trying to replicate the sheer breadth and depth of human intelligence.
So AI's journey has clearly been one of dramatic ups and downs, its springs and winters.
Absolutely, a real roller coaster.
But what's clear is that the foundational seeds of what we now call deep learning were patiently planted and nurtured even during those colder periods.
Yeah, the ideas were there, waiting.
The stage was slowly being set for the next big revolution, a revolution that would ultimately be fueled by the massive increases in available data and raw computing power that were just around the corner. Okay, this brings us to a truly interesting turn of events. Remember those clunky, often frustrating AI systems of the past?
Oh yeah, Clippy, don't remind me.
Right, well, just over a decade ago, something profound shifted. Suddenly, AI began doing things that made us all sit up and take notice.
A real change in the air.
A landmark moment came in 2012 when a Google AI team built a multi-layer neural network with over 1 billion internal connections, 1 billion weights.
1 billion. That's a staggering number.
They let it view millions of random YouTube videos for a week. And astonishingly, without being explicitly told what to look for, it developed a neuron that seemed to specifically encode cats.
The famous Google cat neuron.
Exactly. This self-taught cat recognition machine captured immense public attention and powerfully showcased the burgeoning capabilities of deep learning.
It was kind of a watershed moment, wasn't it, in terms of public perception?
I think so, because it really shifted things. Unlike the frustrating customer service systems, or yes, Clippy, from earlier decades, real-world AI was becoming undeniably noticeable and, frankly, impressive.
Yeah, you started seeing it work in ways that felt different.
While full-blown general AI didn't seem imminent, these dazzling feats were clearly emerging, fundamentally driven by what we now call deep learning.
And this ignited a powerful resurgence of optimism. And of course, a new wave of bold predictions.
There we go again.
Well, yeah. Figures like Shane Legg, co-founder of Google DeepMind, predicted human-level AI will be passed in the mid-2020s.
Mid-2020s, we're basically there now.
Mark Zuckerberg aimed for AI to be better than human level at all of the primary human senses within 5–10 years. And polls of AI researchers suggested a 50% chance of achieving human-level AI by 2040.
So the optimism was back.
Yeah.
Big time.
Huge. And this new AI spring was largely propelled by a specific type of neural network, convolutional neural networks, or convnets.
Convents. Okay, tell us about those.
These networks, initially proposed by Yann LeCun way back in the 1980s, became the absolute driving force behind the deep learning revolution in computer vision.
LeCun, another big name.
Absolutely. Their design was directly inspired by the brain's visual cortex and the early work on neocognitrons.
How do they work, roughly?
Well, convents are ingeniously structured with multiple layers of simulated neurons, or units. Much like how our own visual cortex processes information, units in the lower layers of a convnet detect very simple features, like individual edges or lines.
Okay, basic building blocks.
Exactly. As information progresses up the network's hierarchy, units become sensitive to increasingly complex combinations of these features, perhaps identifying corners, then T-shapes, and eventually whole parts of objects, like an eye or a wheel.
So it builds up complexity layer by layer.
Precisely. This hierarchical detection creates intricate activation maps representing different visual patterns the network notices or is interested in. The core, clever calculation at the heart of these networks, the convolution, which gives them their name, efficiently scans images for these patterns, much like our own eyes do.
But for these convents to truly unlock their potential, they require something truly massive. Enormous amounts of labeled training data.
Right. Data, that's the fuel.
Manually collecting and then labeling millions of images across thousands of categories seemed like an impossible task back then.
Utterly daunting. Until computer scientist Fei-Fei Li made a crucial discovery, Amazon's Mechanical Turk service.
Mechanical Turk, the artificial intelligence.
That's the one. It proved to be a genuine game changer, an ingenious marketplace connecting requesters who need tasks done that are hard for computers with workers, humans willing to lend their intelligence for a small fee.
Named after that old chess hoax.
Exactly. This godsend, as Lee called it, allowed her team to label over 3 million images with corresponding WordNet nouns in just 2 years, thus creating the monumental ImageNet dataset.
3 million images.
Yeah. And today, it's common for academic AI grants to include line items specifically for Mechanical Turk workers. It underscores the vital, often hidden human labor that underpins these seemingly self-learning AI systems.
There's not all magic learning on its own. There's a lot of human effort behind the scenes.
A lot.
This massive dataset then paved the way for the groundbreaking 2012 ImageNet competition. AlexNet, a significantly scaled-up ContNet, developed by Alex Krzyzewski, Ilya Siskiver, and Jeffrey Hinton.
Hinton, another giant, the godfathers of deep learning.
Right. AlexNet achieved an amazing 85% correct accuracy. This was a shocking development at the time, a dramatic leap forward compared to all previous methods.
It blew the competition away.
And its success was largely enabled by the increased computer power, like GPUs, finally available to train its 60 million internal connections using backpropagation.
Yeah, the hardware caught up with the algorithms and the data. The perfect storm.
AlexNet's undeniable success sent a jolt throughout the entire AI community, immediately igniting what was dubbed a ConvNet gold rush.
Everyone wanted in.
Deep learning rapidly became the hottest subfield of AI, with major tech companies furiously hiring experts and funding countless startups. Yann LeCun, the original inventor of ConvNets, was notably lured to Facebook to lead its AI lab.
Big money started flowing.
And this momentum directly led to a proliferation of practical commercial applications. Vastly improved image search, automated photo tagging, Facebook's advanced face tagging, Twitter's content filtering, detection of terrorist imagery, pedestrian tracking for self-driving cars.
Medical diagnoses, too.
right? Even critical medical diagnoses for various cancers and diseases. It truly transformed what computers could see.
But AI isn't just about seeing, it's also about doing.
True. Trying to manually specify every single rule for complex, real-world actions, like programming a robot to load a dishwasher, is virtually impossible. Too many variables.
Infinite edge cases, unpredictable situations, you just can't script it all.
This is precisely where reinforcement learning, or RL, enters the picture.
Right. RL encompasses a broad category of methods where an agent, a computer program, learns flexible strategies on its own by performing actions within an environment and occasionally receiving rewards as feedback.
Learning by trial and error, essentially.
Pretty much. Think of it like training a robot dog, let's call her Rosie, to kick a ball. Rosie learns through trial and error. Her reward is a numerical value whenever she successfully kicks the ball.
So she gets positive feedback for doing the right thing.
Exactly. She gradually builds a mental scorecard, a Q table in some methods, assigning values to actions in different states, learning which ones usually lead to a positive outcome.
What are the key ideas?
Key concepts here involve navigating the balance between exploration, trying new actions to discover potentially better outcomes, and exploitation, using known good actions to maximize reward.
The explore-exploit dilemma.
Right. And also discounting rewards over time to find efficient paths. Due to the inherent complexity and potential risks of real-world training, RL systems are almost always initially trained in elaborate simulations.
Like robots learning to walk in a simulated world first.
Precisely. But transferring these learned skills reliably to the messy, unpredictable real world remains a major stumbling block, the simulation to reality gap.
And this is where DeepMind truly shone, applying reinforcement learning to games.
Yes, their deep Q learning approach ingeniously combined reinforcement learning, specifically Q learning, with powerful deep neural networks.
How'd that work?
Their deep Q network, or DQN, takes the current game state, like the pixels on the screen, as input. It then predicts the value of possible actions, chooses one, and updates its internal connections based on the error, the difference between its predicted value and the actual outcome or reward received after the action. This learning process is often called temporal difference learning.
Okay, learning from the difference over time.
Exactly. Using this innovative approach, DeepMind's system learned to play 49 different classic Atari video games, like Breakout. It often achieved superhuman performance.
Superhuman on Atari games. That's impressive.
And remarkably, it did so solely by observing raw screen pixels without being explicitly programmed with game rules or even concepts of game objects like ball or paddle.
Just from the pixels. Wow.
It even discovered the strategy of tunneling through the bricks in Breakout, an advanced human tactic. This represented a substantial leap forward in machine learning and autonomous problem solving.
But the real showstopper, the moment that truly made headlines worldwide, was AlphaGo's stunning triumph in the game of Go in 2016.
Ah, yes, Go, the holy grail for game AI for a long time.
Why was Go considered so much harder than, say, chess?
Well, Go, despite its simple rules, possesses immense emergent complexity. The number of possible game positions is astronomical, vastly larger than chess, a much bigger game tree.
So brute force search, the kind Deep Blue used for chess, just wouldn't work.
Not feasible. For decades, it was widely believed that it would be 100 years before a computer could beat a human Go champion, largely because the game was thought to rely so heavily on elusive human intuition.
That intuition factor.
Putting this into broader context, AlphaGo's success once again forced us to radically rethink our very definition of intelligence, or at least game-playing intelligence.
How did AlphaGo actually win?
DeepMind's AlphaGo, specifically a later iteration known as AlphaGo Zero, which started with zero human knowledge beyond the basic rules of Go.
Zero human knowledge, just the rules.
Just the rules. It famously defeated world champion Lee Sedol in 2016. It achieved this by combining deep Q learning with a sophisticated Monte Carlo tree search.
Monte Carlo, like the casino. Randomness.
Exactly. This search strategy uses an element of randomness to explore millions of possible moves in the game tree, generating statistics on wins and losses from simulated rollouts or playouts.
Okay.
But crucially, a deep convolutional neural network provided a rough value for likely good moves from any given board position. It essentially acted like an intuition pump, whispering in its ear which paths were most promising to explore further with the Monte Carlo search.
So the ComNet provided the intuition.
Kind of, yeah. And the results from these searches then fed back, continuously training and improving the Convent's evaluation function, its intuition. It learned by playing itself millions of times.
And the same methods worked for other games, too.
Yes, the same core methods adapted slightly, created AlphaZero, which went on to defeat the top computer programs in chess and shogi as well.
It's interesting to note that this achievement harks back to IBM's Deep Blue defeating chess champion Garry Kasparov in 1997.
Right, the first big human versus machine moment in games.
That feat, while incredible at the time, was later kind of re-restricted in our concept of intelligence, wasn't it?
It was. Superhuman chess playing is now largely seen as not requiring general intelligence. Deep Blue, for all its power, had no real conception of what playing a game or winning means to humans. It was a specialized, calculating machine.
The old maxim holds true. As soon as it works, no one calls it AI anymore.
It often feels that way. The goalposts keep moving.
So this again raises a crucial question for us. When we witness AlphaGo's success, are we seeing genuine intuition? Or is it a vastly sophisticated form of pattern recognition and search?
Or does it hint at something deeper altogether? And what does this extraordinary level of machine performance ultimately imply for our understanding of human ingenuity and what we consider uniquely our own?
So what does all this mean for you as an informed observer? We've seen how machines could learn to see and interpret complex visual information.
Remarkable progress there.
Then, they learn to play incredibly complex games at superhuman levels, not by following pre-programmed rules, but by learning autonomously through experience.
Also, truly amazing.
It's genuinely amazing progress. But it also compels us to ask, do these achievements signify that they are truly thinking like us?
That's the profound question, isn't it? Where does performance end and understanding begin? We'll explore that next.
Okay, let's dig into this further. After all those truly impressive feats we just discussed, the vision systems, AlphaGo, you might be thinking, okay, are we almost there? Is true human-level AI just around the corner?
It's a natural question given the hype sometimes.
But as Melanie Mitchell rigorously reminds us in her work, there's a critical distinction to be made between narrow AI and general AI. And the latter, well, still seems very much a distant dream.
This is a really foundational distinction. Despite all the dazzling successes, every AI system to date falls into the category of narrow or weak AI.
What does that mean exactly, narrow AI?
It means they are expertly designed, highly optimized, to perform only one very narrowly defined task, or maybe a small set of closely related tasks.
Like AlphaGo.
Exactly. AlphaGo is the best Go player in the world, but as Mitchell points out, it can't do anything else. It can't even play checkers.
Right. Or Google Translate.
Google Translate excels at translation, but can't tell you if the reviewer liked the movie based on the translated text. It lacks that broader comprehension.
This stands in stark contrast to what people usually mean when they talk about AI in movies, right?
Precisely. That's strong, human-level or general AI, AGI, which is often depicted in science fiction as being able to do most everything we humans can do and possibly much more. Versatile, adaptable intelligence.
And it's not simply a matter of stacking more of these narrow AIs together, hoping they'll collectively achieve general intelligence.
Mitchell argues quite convincingly against that. She says, a pile of narrow intelligences will never add up to a general intelligence. General intelligence isn't about the number of abilities, but about the integration between those abilities.
Integration. That sounds key.
It highlights a fundamental challenge. Current AI approaches, mostly deep learning, struggle with the kind of versatile, integrated understanding, the common sense, that defines human intelligence.
This then begs the question for the AI research community itself, which grapples with considerable controversy over what human-level AI would genuinely entail.
Right, what are we even aiming for?
Would it require consciousness or self-awareness? Are we merely simulating thought, or could machines genuinely be truly thinking?
These are deep philosophical waters.
Alan Turing, with his famous imitation game, the Turing test, proposed an operational definition, didn't he?
He did, suggesting that if a computer could communicate in text so effectively that a human couldn't distinguish it from another human, it should be considered to think.
He called for a plea against meat chauvinism, arguing that intelligence shouldn't be confined solely to biological material.
A provocative idea. But the Turing test itself has revealed some significant frailties in practice.
How so?
Consider the case of Eugene Guzman in 2014, a program posing as a 13-year-old Ukrainian boy.
I remember that. It made headlines.
It managed to fool 33% of judges in a short conversation, leading organizers to claim it passed the Turing test. However, most AI experts hate the Turing test when it's carried out in this manner.
Why?
They often view it as more of a publicity stunt that exploits our very human tendency to anthropomorphize. We, as humans, are perhaps a little too eager to ascribe understanding and consciousness to computers with often very little evidence. We want to believe.
We project intelligence onto them.
Exactly. A good counterpoint is the Kapoor-Kurzweil wager, a $20,000 long bet between software entrepreneur Mitchell Kapoor and futurist Ray Kurzweil.
What's the bet?
Kapoor bet against a computer passing a carefully specified Turing test by 2029. There's stringent rules, for instance, no biological neurons allowed, and requiring judges with expertise clearly show that Eugene Guzman wouldn't stand a chance under such strict conditions.
So the devil's in the details of the test itself.
Absolutely. What constitutes human-level performance can be highly deceptive when the definitions and testing parameters are tightened.
And what about those claims of human-level performance for convnets in image recognition, particularly on ImageNet? Should we take those with a grain of salt, too?
Well, they definitely warrant a closer examination. Statements like, humans have an error rate of about 5% on ImageNet were often based on the performance of a single human, Andrzej Karpathy, a deep learning graduate student at the time.
Just one person.
Yes, who meticulously trained himself on a subset of images and described it as a daunting task. This is hardly comparable to typical effortless human object recognition in everyday life.
That's a really important caveat.
It raises a critical question. When we claim a machine performs better than human, what exactly are we truly measuring? Is it genuinely comparable to human understanding and robustness? Or are we perhaps being misled by statistical correlations and success on narrowly defined tasks?
Like, how do we know it's really seeing a dog?
Exactly. How do we know a ConvNet classifies an image as dog because it actually sees a dog, rather than because it detected a tennis ball or a frisbee that is statistically often associated with dogs in the training data? It might be picking up on superficial correlations.
Has anyone tested this?
Yes. Will Landecker's experiment, for instance, found that a deep neural network classifying images as contains an animal wasn't actually recognizing animals, but rather identifying blurry backgrounds. A simpler cue statistically associated with animal photos in datasets like ImageNet, where photographers focus on the subject.
So it found a shortcut, basically, a statistical trick.
Precisely. It hints that the AI is learning something very different from robust human perception.
This leads us to a deeper, more unsettling issue: the unexpected fragility and overfitting of these systems.
Right. They can be surprisingly brittle. ConvNets trained extensively on web images often perform poorly when presented with images taken by, say, a robot in a different environment. It indicates they can overfit to the specific characteristics and biases of their training data. They don't generalize well to new contexts.
And they're sensitive to small changes.
Very sensitive sometimes. Even superficial changes like slight blurring, adding digital speckles, minor color shifts, or rotating an object can cause ConvNets to make significant errors, even when humans easily recognize the objects without any problem.
That doesn't sound very robust.
It's not. This unexpected fragility strongly indicates that these systems are learning something different from what we're trying to teach them, a pattern recognition that lacks the depth and resilience of human understanding.
Beyond this fragility, there's the pervasive issue of bias within AI systems, a consequence that truly demands our attention.
A huge ethical concern.
A stark example is the Google Photos Gorillas incident in 2015. Can you remind us what happened there?
Sure. A ComNet-powered photo tagging feature mistakenly tagged photos of African Americans as gorillas, leading to a significant public relations crisis and the eventual removal of the tag altogether.
That's awful. How could that happen?
It wasn't intentional malice, but a stark example of how biases embedded in massive training datasets can manifest in deeply problematic ways. If the data underrepresents certain groups, the AI won't learn to recognize them properly.
This is a critical concern because systemic bias, often mirroring societal biases present in the training data, can be inadvertently magnified by AI systems.
And it can do real damage in the real world. For example, face recognition systems are frequently trained on datasets, often collected from online image searches, that are disproportionately skewed. For instance, one large dataset was found to be 77.5% male and 83.5% white,
So the training data doesn't reflect the diversity of the actual population.
Often not. And the American Civil Liberties Union, ACLU, tested Amazon's recognition system.
What do they find?
They found it incorrectly matched 28 members of the U.S. Congress with criminal mugshots. Significantly, 21% of these errors occurred on African-American representatives who constitute only 9% of Congress at the time.
Wow. That clearly highlights a significant higher error rate on people of color.
Which has profound implications for fairness and justice, especially if these systems are used in law enforcement or hiring.
This situation provokes an important ethical discussion. Should AI training data precisely mirror a biased society, or should it be actively tinkered with to promote social reform?
And who ultimately gets to decide that? It's a thorny issue.
Tech companies like Kairos and Microsoft have even voiced their opposition to using face recognition for law enforcement and surveillance, precisely due to its documented unreliability and inherent bias.
Yeah, some are pushing back. As Melanie Mitchell points out, debiasing word vectors is a difficult challenge, but probably not as hard as the alternative, debiasing language and society.
A sobering thought.
Furthermore, deep neural networks are surprisingly vulnerable to what are called adversarial attacks.
Adversarial attacks, what are those?
Researchers have found it surprisingly easy for humans to surreptitiously trick deep neural networks into making critical errors. This is a far more subtle and troubling issue than, say, simply detecting email spam.
No, they trick them.
Well, for instance, they can create images that appear as entirely random noise to human eyes, but a ConvNet will classify them with over 99% confidence as specific objects, like a cheetah or a school bus.
Noise that looks like a cheetah to an AI, that's bizarre.
It is. Or consider specially designed eyeglass frames with specific patterns that can fool face recognition systems into misclassifying the wearer as a completely different person.
Seriously, just by wearing certain glasses.
Yeah. Or small, virtually inconspicuous stickers placed on a traffic sign can cause a self-driving car's vision system to misclassify it. For example, interpreting a stop sign as a speed limit sign.
Okay, that's genuinely scary, the safety implications.
Exactly. And perhaps most critically, researchers have shown that imperceptible alterations to X-ray or microscopy images can cause a medical AI to dramatically change its cancer diagnosis confidence from 99% no cancer to 99% cancer.
Just tiny changes we can't even see.
Tiny targeted changes. These adversarial attacks raise serious alarms not only about the true generalization capabilities of these systems, but also about the potential for costly exploits by malicious actors.
It really shows they're not seeing the world like we do.
It's abundantly clear that something very different from human perception is going on here. If these systems are to be deployed in real-world critical applications, they absolutely must be safeguarded from hackers.
But can they be safeguarded?
Well, defending against such attacks is really hard, often described as a whack-a-mole problem, where patching one security hole often leads to the discovery of others. Ian Goodfellow of Google Brain starkly stated, "Almost anything bad you can think of doing to a machine learning model can be done right now."
It's not reassuring.
Yeah.
So what does this all mean for you, the individual navigating this increasingly AI-driven world?
Yeah, what's the takeaway?
The ease with which AI can be fooled, coupled with this capacity to amplify existing societal biases, truly compels you to question the level of trust we should place in these systems.
Especially as they move into more critical applications.
Exactly, like self-driving cars, medical diagnosis, and even legal processes. It's a call for informed skepticism and rigorous scrutiny. We need to understand these limitations.
And the ultimate problem for AI trustworthiness, Mitchell argues, fundamentally boils down to its lack of deep human-like understanding.
How does human understanding differ?
Humans perceive and understand objects in 3 dimensions, grasping their function, context, and integrating multisensory information. This provides us with robust and flexible recognition.
We see the whole picture.
While humans can be susceptible to visual illusions, our ability to recognize objects in everyday scenes has evolved to be very robust because our survival depends on it. Human perception is also highly regulated by cognition and involves intricate feedback connections in the brain, signals going backwards as well as forwards.
Unlike most current AI models.
Unlike the predominantly feed-forward architecture of most current ConvNets, this crucial distinction suggests that current AI doesn't learn like humans and lacks our intrinsic embodied understanding of the world. It's missing that deeper layer.
Let's turn our attention now to the really nuanced world of language. If you were to ask your virtual assistant, hey, what's the difference between a school bus and an ostrich? What would happen?
Probably just a list of facts about each. It wouldn't get the absurdity.
Exactly. It wouldn't laugh. Because as Melanie Mitchell's insightful restaurant story so eloquently illustrates, language isn't just about words themselves, it's steeped in a rich tapestry of unspoken context, cultural norms, and common sense, precisely where AI often stumbles.
Right, the restaurant story. Can you remind us of the gist?
Sure. It's about a man who orders a rare burger, it comes out burned, he gets angry and storms out without paying the bill, leaving the waitress confused by why he got so bent out of shape.
Okay, a simple scenario, but linguistically complex.
Very. For a computer program to genuinely answer questions about this seemingly simple narrative, it would require sophisticated linguistic skills and substantial knowledge about the way the world works.
What kind of knowledge?
It would need to grasp irony, implicit customs like tipping, the multiple meanings of a word like bill, a check versus proposed legislation, idioms such as bent out of shape, and even nonverbal cues implied by shrugging shoulders.
It's a whole web of understanding.
This kind of understanding triggers what Mitchell calls a common sense cascade, akin to a child's endless why questions about, say, how a bank works, revealing layers upon layers of implicit background knowledge that humans effortlessly take for granted.
The stuff we just know about the world.
Now, in the realm of natural language processing, or NLP, automated speech recognition stands out as deep learning's first major success, arguably one of AI's most significant overall achievements.
Yeah, transcription tech is amazing now. Dictation, virtual assistants.
It has truly revolutionized real-time transcription, and it's incredibly impressive how accurately these systems can convert spoken words into text.
But there's a paradox here, isn't there?
What's that?
The striking paradox is that these systems achieve this remarkable high performance without any understanding of the meaning of the speech they are transcribing.
They hear the sounds, not the meaning.
Exactly. Melanie Mitchell notes her own phone, for example, transcribes "mousse is my favorite dessert" as moose, or bareheaded man as bareheaded man. Hilarious, but revealing errors.
So while highly accurate, these systems are not yet truly at human level in realistic, noisy environments.
No, they remain susceptible to background noise and unusual words. They often struggle with that last 10% of human accuracy in real-world conditions precisely because they lack genuine comprehension of what they're hearing. They don't have the context.
Moving beyond simply transcribing words, let's consider sentiment classification, the task of classifying text, like movie reviews, as positive, negative, or neutral.
Hugely valuable commercially. Businesses want to know what people think.
It offers insights from customer feedback to powering targeted advertisements.
But what's truly illuminating about sentiment analysis is that simple keyword matching is entirely insufficient. You can't just count positive and negative words.
Why not?
Well, a phrase like heavy subject matter might sound negative in isolation, but in the context of a film review, it could actually be a positive descriptor indicating depth.
Ah, context is everything.
It demands capturing the true semantics of words within the context of the whole sentence. This challenge led to crucial innovations like Word2Vec.
Word2Vec. Tell us about that.
Essentially, it encodes words as numerical word vectors. Think of them as coordinates or points in a multidimensional semantic space, where the geometric distance between these points reflects their semantic similarity.
So, similar words are closer together in this space.
Exactly. This idea is rooted in linguist John Firth's principle from the 1950s. You shall know a word by the company it keeps. Meaning, words with similar meanings tend to appear in similar contexts in large amounts of text.
Okay, so it learns meaning from context.
Google's Word2Vec, developed in 2013, utilized a neural network trained on a massive set of documents from Google News to learn these high-dimensional word vectors, maybe 300 dimensions, which are now publicly available.
Then they can do cool things like analogies.
They can even solve some straightforward analogy problems, like the famous man is to woman as king is to queen by doing vector arithmetic. King man plus woman is queen.
That's pretty neat.
But here's a crucial point again. These word vectors, for all their utility, inherently capture the biases present in the language data that produces them.
Oh, right, the bias problem crops up again.
It's pervasive. Because the text data reflects societal biases, the word vectors learn them too. This means they can reflect problematic associations.
Like what?
For example, some models might infer analogies like man is to computer programmer as woman is to homemaker, or find that words associated with women are closer to arts and humanities, while words associated with men are closer to science and engineering.
Yikes. So it encodes stereotypes.
It does. This raises really important questions about fairness and ethical AI deployment. While debiasing these word vectors is a massive technical challenge, as Mitchell suggests, it's probably not as hard as the alternative, debiasing language and society itself.
A huge challenge either way. What about translation? Google Translate seems pretty good these days.
Neural machine translation, exemplified by Google Translate after 2016, also relies heavily on duck learning. These systems typically employ an encoder-decoder architecture using recurrent neural networks, often LSTMs.
How does that work?
They're trained on millions of human-translated sentence pairs. An encoder network reads the input sentence and creates a complex numerical representation, like a thought vector. Then, a decoder network takes that representation and uses it to generate the translated output one word at a time.
And the results? Weren't there claims of human parity?
There were. Some companies initially claimed they were bridging the gap between human and machine translation and achieving human parity.
But reality check.
Melanie Mitchell's own experiments reveal a more complex reality. Her translations of that restaurant story, run through French and Italian and then back into English using Google Translate, produced what she describes as jarring wrong notes and uncomfortably mangled phrases.
Like what?
Like translating rare burger as cooked infrequent, or bill as proposed legislation, or bent out of shape as stooped over.
Okay, definitely not perfect.
The resulting output, while often generally recognizable, was uncomfortably mangled, highlighting a fundamental lack of deep contextual understanding rather than true human-like fluency and comprehension.
It sounds similar for image captioning systems, those AI models that describe pictures.
Exactly. Systems like Google's Show and Tell from 2015 take an image, process it with a convnet, and then generate a descriptive sentence using a decoder network.
And they seemed impressive at first.
They produced accurate captions for many test images, initially dazzling and maybe a bit stunned researchers and the public alike. Microsoft's caption bot even confidently claimed it could understand the content of any photograph.
Understand, that's a strong word.
It is. Because these systems often exhibit what Mitchell calls bipolar performance, they can be incredibly accurate one moment, describing a scene perfectly, and then completely nonsensical the next, hallucinating objects that aren't there.
Unreliable.
And even when their captions are technically correct, these systems don't understand photos in the sense that humans understand them. For instance, a system might accurately caption a picture of a soldier sadly holding a military dog as a man holding a dog, but entirely miss the emotional depth, the broader context, or the deeper meaning of the photo.
It describes the objects, not the story.
Precisely. This fundamental lack of understanding makes these systems inherently untrustworthy in contexts where true meaning and nuance are critical.
So, the ultimate dream of natural language processing, the Star Trek computer, a system that genuinely understands what you are asking and provides just the right chunk of response, that's still sci-fi.
Largely elusive, yes. Today's virtual assistants, like Siri or Alexa, can transcribe speech with impressive accuracy, but they fundamentally don't comprehend the meaning of most questions beyond simple commands or information retrieval.
They fail on common sense.
Notoriously. They fail on even simple common sense queries like, does Usain Bolt know how to run? Or can a fish drown?
What about IBM Watson on Jeopardy? That seemed like understanding.
Watson's victory in 2011 was certainly a marvel of engineering. It combined many advanced AI methods like NLP parsing, incredibly rapid database search, sophisticated confidence scoring, and was extensively trained on vast archives of Jeopardy clues.
It could answer tricky clues.
It could. It answered complex, pun-laden clues like even a broken one of these on your wall is right twice a day, correctly identifying what is a clock.
Impressive. But were there limitations?
Oh, yes. It also made head-scratching errors, like famously answering a question in the U.S. cities category with what is Toronto, or guessing Baby Ruth Ginsburg. And ironically, it completely didn't get the joke of Ken Jennings' humorous, I, for one, welcome our new computer overlords concession.
So not really understanding the nuances.
Many critics deemed it more of a highly impressive publicity stunt or a sophisticated parlor trick, effective due to Jeopardy. Maybe specific question-answer format and massive training data rather than any genuine human-like understanding.
Okay. So how do researchers test for deeper understanding now?
Well, benchmarks like SQUAD, Stanford Question Answering Dataset, have emerged. Here, AI reads a paragraph and has to extract the answer, which must be a direct phrase copied from the text.
So it's text extraction, not generation or inference.
Right. While deep neural networks achieve high scores, this task deliberately avoids requiring higher-level understanding or the interpretation of implied messages. It tests reading comprehension in a very constrained way.
What's a harder test then?
The true test of common sense for AI arguably comes with what are known as Winograd schemas.
Winograd schemas, you mentioned these earlier. How do they work again?
They are particularly clever. They are pairs of sentences, identical except for a single word, which subtly flips the reference of a pronoun like it or they.
Give us that example again.
Sure. The city council refused the demonstrators a permit because they feared violence. Here, they clearly refers to the council. Compare that to the city council refused the demonstrators a permit because they advocated violence. Now, they clearly refers to the demonstrator.
Okay. One word changes who they is.
Exactly. These are easy for humans but tricky for computers because solving them requires genuine common sense knowledge, like knowing that uncles are generally older than their nephews, or that if a table won't fit through a doorway, it's the table that's too wide, not the doorway. Basic world knowledge.
How well do computers do on these?
Currently, the best programs tackling these schemas achieve only about 61% accuracy. While better than random guessing, 50%, this is still far from human performance, which is virtually 100%.
So still struggling significantly.
And these programs largely rely on statistics of subphrases. For instance, counting how often certain phrases appear together in vast amounts of text via Google search, rather than true reasoning or understanding.
Finding correlations, not causation or meaning.
As Oren Etzioni, director of the Allen Institute for AI, humorously quipped, when AI can't determine what it refers to in a sentence, it's hard to believe that it will take over the world.
Good point.
Putting this in a broader context, all these examples, from speech recognition's superficial brilliance to the Winograd schemas exposing AI's common sense vacuum, strongly suggest that human-level language processing, true understanding, remains a distant goal.
It really questions our definition of understanding.
Absolutely. And it's worth noting, just like computer vision, NLP systems are also vulnerable to adversarial attacks. Researchers can make imperceptible alterations to text paragraphs that cause question-answering systems to give completely wrong answers, further highlighting their fragility and the absence of genuine comprehension.
So if machines are struggling with common sense and true understanding, what are the essential building blocks of human understanding? Where does our intelligence come from?
That's the million-dollar question. Melanie Mitchell argues that we humans possess an essential body of core knowledge, partly innate, partly learned very early in life.
Like what kind of core knowledge?
This includes fundamental concepts like object permanence, the understanding that the world contains distinct objects, that their hidden parts still exist, and that their parts generally move together.
Stuff babies learn very early.
Exactly. Also, intuitive physics, knowing how objects generally behave. Pushing makes things move, dropping makes things fall. Objects don't simply disappear or pass through each other. We grasp cause and effect naturally.
And biology.
Yes, intuitive biology. Understanding how living things fundamentally differ from inanimate objects. For instance, knowing a dog moves of its own accord and can see, hear, and smell, unlike a rock. This knowledge is deeply ingrained, mostly subconscious.
We just know it without thinking about it.
Furthermore, humans are adept at forming mental models of situations. We can run simulations in our minds to predict outcomes or imagine alternatives. Douglas Hofstadter vividly described this as an implicit counterfactual sphere, a halo of possible variations surrounding any situation we encounter.
Like imagining what if.
Exactly. This allows us to mentally put ourselves in the woman's role, in a driving scenario, for instance, and predict likely behaviors based on her perceived goals and the situation.
And then there are metaphor and analogy. You mentioned these are really important.
Hugely important and often overlooked. They're not just poetic devices for spicing up language. They are fundamental to human cognition. Cognitive scientists George Lakoff and Mark Johnson argue that we understand many abstract ideas largely through physical metaphors, concepts like argument is war, ideas are food, love is a journey.
We map abstract concepts onto physical experiences.
Precisely. Psychologists have even shown that simply thinking about physical warmth, like holding a hot cup of coffee, activates the same brain area as thinking about social warmth and can actually influence how we rate a stranger's personality as warmer.
Wow, that's fascinating. The physical and abstract are linked.
It supports the idea that our understanding is deeply rooted in the mental simulation of sensory motor states. It echoes Hofstadter's concept of a strange loop of consciousness, where symbols seeming to have free will push particles around. It's this circular causality where our physical sensations can activate abstract concepts and vice versa, suggesting a profound intertwining of body and mind in shaping intelligence.
Another crucial element is our ability for abstraction, and what Mitchell calls the subtlety of sameness.
Explain that.
From infancy, we are constantly abstracting concepts. Distinguishing happy from sad faces at 3 months, understanding a bye-bye wave means someone is leaving at 6 months, categorizing cats and dogs by 18 months.
Learning categories and concepts.
Later, we grasp letters by age 3, understand complex social situations like a caregiver can forget a child by age 8, discern musical styles by 16, and even understand complex linguistic suffixes by 20. This continuous ability to perceive the subtlety of sameness across different contexts, to see the underlying concept, is utterly fundamental to human learning and understanding.
And AI struggles with this kind of flexible abstraction.
Profoundly. This is starkly highlighted by Bongard problems, those visual puzzles designed by Mikhail Bongard back in 1967.
Right, the difference, puzzles for concepts.
Exactly. These puzzles challenge our ability to perceive subtle, often abstract concepts that distinguish two sets of 6 images. For example, a set where all objects are large versus one where they are small, or identifying an object with a constriction as the common theme.
How do current AIs do on those? Current concepts, despite their incredible visual prowess on ImageNet, perform only slightly better than random guessing on these problems. It clearly demonstrates their inability to perform human-like abstraction and analogy on the fly.
They can't grasp the underlying concept easily.
Similarly, Douglas Hofstadter's own microworld for studying analogy, called Copycat, which used simple letter string puzzles, like if ABC changes to ABD, what does IJK change to, revealed what he termed conceptual slippage, where concepts from one situation fluidly slip to related ones in another. It showed how analogy can trigger a cascade of mental slippages, often evoking physical metaphors, a process current AI largely fails to replicate.
This raises a profound question for all of us. Can machines truly understand without the foundational capacities for common sense, mental simulation, metaphor, and abstraction that we humans possess?
Capacities that seem deeply rooted in our embodied experience and our developmental learning trajectory from childhood.
Exactly, which leads to the embodiment hypothesis.
Right. A small but growing segment of the AI community argues that human-level intelligence cannot be achieved without a physical body that interacts with the world. They suggest that disembodied computers, or even a hypothetical brain in a vat, would simply lack the necessary grounding for concepts like up, down, heavy, warm, which are fundamental to our common sense and metaphorical thinking.
So if machines aren't learning common sense organically through embodied experience, can we simply program it in? What about projects like Psych?
Ah, Psych. The Psych project, initiated by Douglas Hofstadter way back in the 1980s, represents the longest-lasting and most ambitious attempt to hand-code common-sense knowledge into machines as logical assertions. Millions of rules about the world.
What's the philosophy behind it?
Psych's underlying philosophy, much like early symbolic expert systems, rests on the belief that intelligence can be fully captured by human-programmed rules operating on a sufficiently extensive collection of explicit knowledge. It currently boasts around 15 million assertions.
15 million? That sounds like a lot.
It is, but Lehnes himself estimated that this is only about 5% of what we ultimately need for true common sense.
Only 5%. Wow. That's a monumental task.
And there are deeper limitations. A significant portion of our human common sense, particularly that intuitive physics and biology we talked about, operates largely subconsciously and simply cannot be explicitly articulated and programmed by human experts. We don't even know how we know it.
Right, the subconscious knowledge problem again.
Moreover, Psych's logical inference systems struggle to capture the fluid, flexible, human-like abilities for abstraction and analogy making. Its reasoning is much more rigid.
So what's happened with Psych?
Much like IBM's Watson, Psych has ultimately found its commercial niche in specialized domains, providing knowledge bases for specific applications, remaining narrow rather than general in its focus. Its actual general common sense capabilities lack transparency and don't seem close to human level.
So manually building an understanding seems incredibly difficult, maybe even impossible for the subconscious parts.
The Psych effort really underscores the immense difficulty of that approach. It seems understanding might need to emerge, not just be programmed.
Okay, so as AI continues to become more powerful and deeply embedded in our lives, from identifying our faces in photos to potentially driving our cars, we're forced to ask harder questions.
Yeah, it's not just can it work anymore.
Exactly. We're not just asking if it works, but if it works ethically, fairly, and safely. This brings us to what's often termed the great AI trade-off.
The trade-offs.
Andrew Ng, another prominent AI researcher, optimistically declared, AI is the new electricity, envisioning its transformative impact across nearly every industry. Huge potential benefits.
Right. But what truly stands out about this comparison, as Mitchell notes, is that unlike electricity, which was profoundly well understood scientifically before its widespread commercialization.
We knew the physics.
Right. We are now deploying AI systems whose behavior we still struggle to fully predict or even explain. That black box problem.
So what level of risk are we, as a society, willing to accept for the promised benefits of AI? Especially when we know the underlying understanding of these systems is so fundamentally different from our own.
That's the core dilemma. Should we wholeheartedly embrace the abilities of AI systems, pushing for rapid deployment despite their documented unpredictable errors, susceptibility to bias, vulnerability to hacking, and inherent lack of transparency? Or should a more cautious approach be warranted? This debate directly influences the extent to which humans must remain in the loop across various AI applications. How much autonomy do we grant them?
Affecting everything from self-driving cars to critical medical systems to loan applications.
Absolutely. It's a society-wide question.
Beyond this overarching trade-off, we face increasingly complex ethical dilemmas, particularly with the widespread deployment of face recognition technology.
Yeah, that's a really hot topic.
Its ubiquity, from social media platforms like Facebook automatically tagging us, to its use by law enforcement, raises significant privacy concerns for everyone. Are we okay with being constantly identified everywhere?
And beyond privacy, these systems exhibit concerning unreliability and inherent bias, as we discussed earlier.
Right, the ACLU test on members of Congress.
Exactly. Demonstrating that face recognition technology can have a significantly higher error rate on people of color than on white people. This disproportionate error rate can lead to severe consequences, including wrongful accusations or the denial of essential services.
And some tech companies are pushing back.
Yes, some, like Kairos and Microsoft, have themselves voiced opposition to the use of face recognition for law enforcement and surveillance, specifically citing these issues of unreliability and bias. This necessitates serious consideration about how we allow such powerful yet demonstrably flawed technologies to be deployed.
It's a messy ethical landscape. And what about the concept of moral machines? Can AI develop its own sense of morality and make ethical decisions autonomously?
The robot ethics question. It inevitably brings up scenarios like Isaac Asimov's famous laws of robotics.
Don't harm humans, obey orders, protect yourself.
Right. But as Asimov's own stories brilliantly illustrate, robots can't reliably follow even seemingly simple ethical rules like avoid harming a human without first deeply understanding the concept of harm in different situations. What constitutes harm? Is inaction harm? It gets complicated fast.
Requires common sense again.
Genuine moral reasoning requires a profound level of cognitive ability, understanding cause and effect, the capacity to imagine future outcomes, inferring the beliefs and goals of others, theory of mind, and accurately predicting the consequences of actions.
All fundamental aspects of general common sense that are currently missing in AI.
The classic trolley problem, often discussed in relation to self-driving cars, perfectly highlights these difficult ethical dilemmas.
Swerve and hit one person, or stay straight and hit 5.
Exactly. An autonomous vehicle might be forced to choose between two catastrophic outcomes in an unavoidable accident. How do you program that choice? Attempts to program explicit moral rules or trying to have machines learn moral values on their own by observing human behavior both face significant problems.
Like biases in human behavior itself.
Precisely. Or the sheer complexity of moral situations. It seems moral reasoning is prerequisite on having general common sense.
Let's shift gears slightly. What about the impact of AI on jobs? Will artificial intelligence lead to massive unemployment, as some dire predictions suggest?
The honest answer, according to Mitchell and many others, is that no one truly knows for sure, because the future capabilities of AI remain inherently unpredictable.
We don't know what it will be capable of in 10 or 20 years.
Exactly. And remember, the easy things are hard principle. Many human jobs that we might intuitively think are simple, requiring dexterity or social interaction or common sense, are in fact still considerably harder for computers and robots to perform effectively than we might imagine.
Like folding laundry reliably.
Or having a nuanced conversation. Historically, new technologies have often created entirely new job categories, even as they render older ones obsolete.
Like web developers didn't exist 40 years ago.
Exactly. So the burgeoning field of AI ethics could, quite ironically, create numerous jobs for moral philosophers or AI auditors or data labelers.
That's an interesting twist.
It's also worth noting that AI has already begun replacing humans in low-wage jobs that are boring, exhausting, degrading, exploitative, or downright dangerous. Think robots in factories doing repetitive tasks, or potential self-driving trucks for long hauls, or robots for environmental cleanups.
So automation can have benefits too.
Absolutely. It often is to society's overall benefit, freeing humans from undesirable or unsafe labor. This points to a complex, uncertain impact on the workforce rather than a simple, clear-cut disaster scenario. It's about transition and adaptation.
And what about creativity itself? Can machines truly be creative? We touched on EMI earlier.
Right. Examples such as Carl Sims's computer-generated evolving art or David Cope's EMI music show that creativity often emerges from a kind of teamwork of human and computer.
How does that teamwork function?
In these scenarios, the computer typically generates vast variations or possibilities based on rules or data, and the human provides the critical judgment, the taste, grounded in an understanding of abstract artistic concepts and goals.
The human is the curator, the director.
Putting this into broader context, while EMI produced music that famously fooled professional musicians into thinking it was Bach or Chopin.
Which is pretty amazing.
It is, but Melanie Mitchell rigorously argues that the program itself wasn't truly creative. It relied heavily on Cope's deep musicological knowledge, his understanding of composers' signatures, musical grammar, and rules, along with random number generation to generate variations within those constraints.
So Cope provided the intelligence and structure.
Exactly. EMI, crucially, had no real understanding of the music it generated and could not judge the quality of its own music. That was entirely Coe's job. This is a critical distinction. The human provides the deep understanding, the aesthetic judgment, and the ultimate artistic intent, a role machines have yet to genuinely emulate. They're powerful tools, but maybe not creators in the human sense.
So what does this all mean for you, the listener? As AI becomes increasingly ubiquitous, we're compelled to ask not just if it works, but if it works ethically, fairly, and safely.
Yeah, the how and why become just as important as the what.
And time and again, the answers seem to lead us back to that elusive yet fundamental quality understanding, or the profound lack thereof in today's machines.
It's the recurring theme.
Finally, let's turn to the ultimate big picture, a vision that captivates and concerns many: the singularity.
Ah, Kurzweil's vision again.
Ray Kurzweil's prediction of the singularity arriving by 2045, where non-biological intelligence becomes 1 billion times more powerful than all human intelligence, is premised on a belief in continued exponential progress. Moore's law forever, basically.
This fuels the dramatic idea of an intelligence explosion, where an artificial general intelligence rapidly improves itself, becoming superintelligent by shedding what are considered human limitations.
What limitations?
Things like our slowness of thought, our irrationality, our messy emotions, our need for sleep.
So the idea is AI becomes pure, super-rational intelligence.
That's the common sci-fi trope. But Melanie Mitchell, however, offers a compelling counter-argument, suggesting a different, perhaps more grounded future.
What's her take?
She finds it more likely that these supposed limitations of humans, our physical bodies, our emotions, our irrational biases, our complex social functioning, are in fact part and parcel of our general intelligence.
So our flaws are actually features.
Possibly essential features. She posits that these traits are precisely what enable us to be generally intelligent rather than narrow savants, like current AI systems. Essentially, she suggests that general intelligence can't be separated from all these apparent shortcomings, and may, in fact, be dependent upon them. You can't have the intelligence without the embodiment and the emotion.
That's a really provocative thought. Intelligence isn't just calculation.
So her ultimate perspective on how terrified we should be is quite nuanced and practical. She argues that superintelligent, conscious machines are not on the horizon. The hype is overblown.
So don't worry about Skynet just yet.
Probably not. The aspects of our humanity that we truly cherish, our creativity, our empathy, our unique ways of understanding the world, are simply not going to be matched by a bag of tricks, as she puts it, referring to current deep learning techniques.
So what should we worry about then?
Rather, for Mitchell, the more immediate and tangible worries are things like massive job losses due to automation, the potential for misuse of AI systems like surveillance or autonomous weapons, and these systems' ongoing unreliability and vulnerability to attack, issues that are already present or emerging right now. Practical, near-term risks.
And she also highlights Douglas Hofstadter's deeper, more existential fear. Right?
Yes. His terror, stemming from EMI, wasn't just about superintelligence. It came from the idea that human cognition and creativity would be too easily matched by AI programs, and that the sublime creations of the human minds that he most revered, Chopin, for example, might be trivialized by a small chip.
A devaluing of human genius.
Exactly. This potential emotional impact on our perception of humanity and our unique value was his core concern. Will we feel less special if a machine can compose like Bach? Despite these complex fears, Mitchell ends on a slightly hopeful note, seeing a growing and encouraging sense of cooperation and common purpose that is emerging among researchers, corporations, and politicians on the urgency of reckoning with these ethical and societal issues.
So there's growing awareness of the need to manage AI responsibly.
Putting this into broader context, this entire deep dive truly boils down to what we value about our own intelligence. Are our human foibles, our emotions, our biases, our physical experience, the very things that make us generally intelligent, or are they simply obstacles for machines to eventually overcome?
It really encourages critical thinking about these core assumptions.
And about what it genuinely means to be human in an increasingly AI-driven world. #tag outro.
We've truly journeyed through a remarkable landscape today. We have explored AI's optimistic, sometimes wildly optimistic, beginnings.
Yeah, those early predictions.
Weathered its historical winters, celebrated its current impressive springs, marked by stunning advancements in computer vision and gameplay,
The deep learning revolution.
and critically confronted its profound limitations in areas like true understanding, robustness, and ethical fairness.
The shadow side.
We've come to see that while AI excels at specific, often incredibly complex tasks, the seemingly easy things like common sense, abstract reasoning, and genuine comprehension remain remarkably hard for machines.
The paradox of AI.
At its heart, the great AI trade-off remains a constant and evolving negotiation.
Yeah. Balancing the potential and the risks.
It's the tension between AI's immense potential to improve our lives and the inherent risks of deploying systems that fundamentally lack human-like understanding, making them unpredictable, susceptible to bias, and vulnerable to manipulation.
A conversation we need to keep having.
So what does this all mean for you, the thinking human navigating this rapidly evolving world? It's clear that the answers aren't simple, and perhaps the most compelling questions AI raises are ultimately about the very nature of our own humanity.
It holds up a mirror to ourselves.
It really does. Which leads us to a crucial question for all of us. As we continue to delegate more tasks and responsibilities to artificial intelligence, what aspects of our own unique intelligence do we risk taking for granted, or even inadvertently devaluing if we don't fully grasp what understanding truly means?
That's something to really mull over.
And if any computers happen to be reading this transcript, tell me what it refers to in the previous sentence.
Ha! Good luck with that one.
Because until then, the quest for true understanding and the profound ability to ask why remains uniquely ours.
Commercial bakeries can benefit from the additional working capital factoring can provide. Contact Chris Lehnes at Versant Funding to learn if your client is a factoring fit.
Okay, picture this. You're at the Googleplex. The heart of Google, this hub of information. And our source materials author, she actually got completely lost.
Oh, really? Where?
Inside the Google Maps building itself. Can you believe it?
Wow. That's pretty ironic.
Irony squared, she called it. And it kind of perfectly sets the stage for our deep dive today into artificial intelligence. We're going to, pull back the curtain a bit. What is AI really? What can it actually do right now? And what's truly on the horizon?
Exactly. Look, our mission today is really to get past the headlines, the hype. We want to uncover let's say, the true state of AI. Where's that gap between the big promises and the reality on the ground? And crucially, what does all this mean for us, as thinking humans navigating this world?
Right. So think of this as a journey. We'll trace AI's evolution, look at some, frankly, surprising breakthroughs, but also confront its current very real limitations and explore those big questions it raises about our own intelligence. The goal here is for you to walk away with a clearer, more nuanced picture. And speaking of those big questions, something that really jumped out from the sources was Douglas Hofstadter's view.
Ah, Hofstadter.
Oh.
Gödel, Escher, Bach. a legend.
Exactly. A pioneer, an early believer in AI's potential. But at this Google meeting, he expressed this deep ambivalence. He even used the word terrified.
Yeah, but it's key to understand what terrified him. It wasn't like the Terminator scenario, rogue AI taking over.
Right.
His fear was more subtle. It was about the potential trivialization of human creativity, of our intelligence, the spark that makes us human, by what he called superficial algorithms.
That's a really important distinction. It sets a thoughtful tone.
It really does.
So let's rewind. Where did this all officially begin? People usually point to Dartmouth College in 1956.
That's the one, the Dartmouth Workshop, where John McCarthy actually coined the term artificial intelligence.
And he did that specifically to distinguish it from cybernetics, right?
Precisely. He wanted a new banner, a focused field.
And the optimism back then.
Yeah.
Wow, even with computers that were, what, 1,000,000 times slower than our phones?
Oh, absolutely. You had pioneers like Herbert Simon, Marvin Minsky, making these incredibly bold predictions.
Simon thought machines could do any work a man can do in 20 years.
And Minsky was even more ambitious. He said, within a generation, the problems of creating artificial intelligence will be substantially solved. They really thought they were close.
It's amazing. But they immediately hit a wall, didn't they? This fundamental problem.
Defining intelligence itself, yeah. Minsky called it a suitcase word.
A suitcase word.
Meaning you just cram all sorts of different things into it, thinking, cognition, consciousness.
Yeah.
AI basically just inherited that whole definitional mess.
Okay. So with all that buzz and this, well, fuzzy definition, two main paths sort of emerged.
That's right.
The first was symbolic AI. Can you maybe explain that a bit?
Sure. Think of classic logic puzzles. Missionaries and Cannibals is a good example. Symbolic AI programs worked by encoding things like missionary or riverbank as, well, abstract symbols.
Okay. And then the computer just manipulates these symbols based on rules we give it.
Exactly, like the boat holds two people. The machine follows the rules, solves the puzzle, but, and this is crucial, it has absolutely zero understanding of what a missionary or a cannibal is. It's just symbol shuffling.
Right. It's just following instructions, essentially.
Pretty much.
Yeah.
Powerful for defined problems, but it struggled with, the real world's messiness.
Which led to the other path.
So symbolic AI. This was more inspired by neuroscience, by how the brain might work. Think early neural networks, perceptrons. These aren't based on human-readable rules. They learn from data. Lots of data.
Yeah.
They use complex math to find patterns, adjust themselves.
Kind of like learning by example rather than by rules.
In a way, yes. But for decades, symbolic AI was really dominant. People were pretty skeptical about the sub-symbolic stuff.
Especially after that book, Perceptrons, by Minsky and Paper in '69.
Oh, yeah. That book basically proved the mathematical limits of those early simple neural nets. It poured cold water on the idea for a while.
And that led to the first AI winter.
It did. You see this pattern in AI history. Huge promises, media frenzy, then disappointment when the breakthroughs don't quite materialize. Funding gets cut. By around 1990, artificial intelligence was almost a dirty word. Researchers were actually told to avoid using it.
Wow. But like a stubborn plant, the idea didn't completely die out.
Not at all. A dedicated group kept working on neural networks. And in the late 70s, early 80s, they had a key breakthrough.
Which was?
The backpropagation algorithm. This was huge. It finally gave multi-layer neural networks a way to learn effectively, to adjust their internal connections based on their mistakes.
Ah, so they could actually learn from complex data now.
Right. This revived the field, leading to what became known as connectionist networks. There was this influential book in '86, Parallel Distributed Processing.
The Bible of connectionism, wasn't it?
Pretty much. It argued these brain-inspired networks were way better for things humans do easily, like perception, language, things that need that sort of subconscious common sense. It was a direct challenge to symbolic AI's brittleness.
And fast forward a bit. That persistence really paid off, didn't it? Takes us to, what, 2012?
Indeed. The current AI spring, as some call it, that Google project was a big moment.
The one where the neural network watched YouTube videos.
That's the one. Millions of random videos.
Yeah.
And the network all by itself learned to recognize cats. Nobody explicitly programmed catness into it. It just figured it out from the data.
That's genuinely amazing. And that's deep learning, right?
Exactly. That and most of the big AI achievements you hear about today, they're powered by deep learning. It's basically a sophisticated set of neural network techniques.
But to get these things to work, you need massive amounts of data, like for computer vision, the ImageNet competition.
Oh, ImageNet was crucial, yeah. Labeling 1.2 million images across 1,000 categories. I mean, think about that task.
How on earth did they manage that?
Well, here's where something else comes in. Something often hidden. Amazon Mechanical Turk.
Mechanical Turk. Sounds odd.
It's sometimes called artificial intelligence. Basically, you have tens of thousands of people globally doing small online tasks for small payments. Pennies per photo, sometimes.
So humans were labeling the images.
Yep. Tasks that are easy for us, is this a cat?
Yeah.
But still incredibly hard for computers. It highlights the huge amount of human labor that actually underpins a lot of AI progress.
Right, that's quite something. And with that labeled data...
Come 2012, the ImageNet competition, a system called AlexNet, a type of deep learning network called a convolutional neural network, or ConvNet.
What did it achieve?
It got 85% accuracy on object recognition, which sounds okay, but it absolutely crushed all the other competing methods. It was a shock.
And that sparked the current boom.
Pretty much ignited a gold rush for deep learning experts. Yeah. Suddenly everyone wanted in.
Okay, so breakthroughs like AlexNet, AlphaGo beating Go champions, impressive stuff. But we need some perspective here. This is where the narrow versus general AI distinction comes in, right?
Absolutely critical distinction. Everything we have today, even AlphaGo, the world's best Go player, arguably.
Yeah.
It's all narrow or weak AI.
Meaning?
Meaning it's incredibly good at one specific thing. AlphaGo is a Go genius. But ask it to play checkers. It can't. Ask it what winning feels like. No clue.
And the feeling among many experts is that just piling up lots of these narrow AIs, it won't suddenly create a general intelligence, right?
That's a widely held view, yes.
Yeah.
A pile of specialized tools doesn't magically become a general-purpose thinker.
So when we see headlines like AI surpasses human-level performance, especially in things like object recognition, we should be a bit skeptical.
Definitely take them with a grain of salt. For example, that human error rate on ImageNet people compared AI to, often that was one specific researcher, Andrei Karpathy, who trained himself like crazy to label images super fast.
Hardly representative of, average human vision.
Yep.
Not at all. And even when these contents do recognize objects, they might not be seeing them like we do.
How so?
They might latch on to statistical correlations. Like maybe dogs in the training data often appear with tennis balls. So the network learns to associate tennis balls with dogs rather than recognizing the dog's form itself.
Huh. And they can overfit too, learn the wrong cues.
Exactly. Like learning that blurry backgrounds often mean there's an animal, even if the animal isn't clearly visible. And their fragile, tiny changes, a slight blur, a color shift humans wouldn't notice, can completely fool them.
Which can lead to some moments like that Google Photos incident back in 2015.
Yes. The system tagging photos of African Americans as gorillas. A truly awful example.
What causes that kind of catastrophic error?
It starkly illustrates bias in AI. The problem often starts with the training data. If your data set for facial recognition is, say, 77% male and 83% white,
Which reflects existing societal biases.
truthfully, then the AI learns those biases. And when deployed, it can amplify them. Look at the ACLU test of Amazon's recognition.
They tested it on members of Congress.
Yeah. It falsely matched 28 members with criminal mugshots. And disproportionately so for African-American representatives. 21% of the errors were on them, though they were only about 9% of Congress. Shows how bias baked into data has real-world consequences.
That's deeply concerning. And if that wasn't enough, there's this other issue, that these networks can be deliberately tricked.
Oh, absolutely. This vulnerability to adversarial attacks is, frankly, quite startling.
What kind of tricks are we talking about?
Well, researchers can create images that look like meaningless static to us.
Just noise?
Yeah, random noise.
Yeah.
But AlexNet will classify it as, say, a cheetah with over 99% confidence.
No way.
Or designing special eyeglass frames that make facial recognition systems fail completely. Even simpler things, putting carefully designed stickers on a stop sign.
And a self-driving car sees it as something else.
Misclassifies it as a speed limit sign, for instance.
Yes.
And maybe the most worrying, tiny, imperceptible changes to medical scans that cause an AI to diagnose cancer where there is none or miss it when it's there.
Good grief. That sounds like you're constantly playing defense, trying to patch vulnerabilities, a whack-a-mole problem, as the source calls it.
It really is. There's no single general defense. And it forces you to ask, what are these networks actually learning? If they're so easily fooled by things we don't even see, how deep can their understanding really be?
Okay, let's shift gears a bit. Language. Speech recognition, I mean, that feels like a huge AI success story, right? My phone gets me pretty well most of the time.
It's definitely one of the most significant successes, yes. Accuracy in quiet environments can be remarkable.
But there's always a but.
The but is that it's transcription without comprehension. It turns sounds into words, but doesn't grasp the meaning.
Give me an example.
Well, you might say, mouse is my favorite dessert, and it hears, moose is my favorite dessert. Or, the bare-headed man becomes the bare-headed man. Sounds right, but the meaning is lost because it lacks common sense. Background noise, unusual phrases also trip it up badly.
Right, those nuances. And that lack of understanding becomes even clearer when you look at things like sentiment classification. Yeah. Figuring out if a review is positive or negative.
Exactly. You can't just count words like dark or horrific. Context is everything. Enough humor to keep it from becoming too dark. Suddenly dark isn't negative.
So how do systems try to handle that complexity?
One powerful technique is word embeddings, like word2vec. It's based on the idea, you shall know a word by the company it keeps.
Meaning words that appear in similar contexts get linked?
Essentially, yes. They get represented as numbers, vectors, in a way that words used similarly are numerically close to each other. Hated and abhorred could be close. It helps capture some semantic relationships.
Another but.
The downside is these vectors learn the biases present in the text data they're trained on.
Like the example, man is to woman as computer programmer is to.
Tomemaker. That was an actual result from Google's system at one point. The AI simply reflects the societal biases embedded in the billions of words it read.
Wow. And this lack of deeper understanding shows up in translation too.
Oh, definitely. Machine translation like Google Translate is amazing, but it often produces text that's, as the source puts it, recognizable but uncomfortably mangled. It trips up on idioms or words with multiple meanings like build restaurant check or legislative proposal.
And image captioning. Sometimes it seems okay.
It can often get the basic objects right, a man holding a dog, but it frequently misses the meaning of the photo, the context, the emotion, the story.
Which brings us to the ultimate sci-fi dream, the Star Trek computer. Just ask it anything. How close are we? Siri, Alexa.
They're great at transcription, like we said, and pulling up facts, but common sense reasoning.
Yeah.
Still a huge gap. Ask Alexa about Usain Bolt's records, fine. Ask, does Usain Bolt know how to run fast? And it's stumped. Sorry, you don't know that one.
It lacks that basic world knowledge.
Precisely. Which raises questions about things like IBM Watson winning Jeopardy.
That seemed like a massive leap.
It was an incredible feat of engineering, no doubt. Broad knowledge, super fast search. But it was also highly specialized, trained specifically for the Jeopardy format, on vast amounts of text, including past clues. Some debate whether it was true general intelligence or, well, a very impressive but targeted publicity stunt.
And this common sense gap, it's really highlighted by those Winograd schemas, isn't it?
Yes, they're brilliant for showing this.
Yeah.
Those sentence pairs, identical except for one word that flips the meaning entirely.
Like, the city council refused the demonstrators a permit because they feared violence versus because they advocated violence.
Our common sense instantly tells us who they refers to in each case. The council feared, the demonstrators advocated.
But AI struggles with this.
Massively. Current systems are way below human accuracy. They often rely on statistical tricks, like guessing based on which phrasing is more common online, rather than actually understanding the situation. As one expert joked, if AI can't figure out what it refers to, maybe we don't need to worry about it taking over the world just yet.
Fair point. So what is it about us humans? What allows us to handle this common sense stuff so easily?
A big part seems to be our core knowledge. This deep, often unconscious understanding of how the world fundamentally works.
Like intuitive physics, knowing things fall down.
Exactly. Intuitive physics, intuitive biology, knowing living things move intentionally, and intuitive psychology, understanding that others have goals, beliefs, feelings. AI generally lacks this foundational layer.
And we use this foundation to build mental models, right? Simulate things in our heads.
We do, even abstract concepts. That's why metaphors resonate. Warm welcome, icy stare. We map physical sensations onto social or emotional ones. That study where holding a hot coffee made people judge someone as warmer. That's it, in action.
It's all connected to our physical experience.
Very much so. And Hofstadter argues that analogy is the absolute core. Without concepts, there can be no thought. And without analogies, there can be no concepts.
We build understanding by comparing things, finding similarities.
Constantly. Think how kids learn. Abstracting waving, figuring out the concept of dog from different examples.
And those Bongard problems Hofstadter designed were meant to test exactly that, right? Seeing abstract similarities.
Precisely. Those visual puzzles. 6 images on the left share a concept, 6 on the right share a different one. You have to grasp the subtlety of sameness. Maybe it's concave versus convex, or something more abstract like having a neck.
Humans are good at this on-the-fly concept formation.
Remarkably good. Current AI, not so much. It really struggles with forming novel abstractions like that.
Okay, so this brings us back to that Obama picture analysis you mentioned earlier, the one by Andrej Karpathy.
Right. Obama's secretly putting his foot on the scale someone's using. Karpathy pointed out all the layers a human instantly processes. The 3D scene, intuitive physics, way will go up, but also mind reading. Inferring the other man's unawareness, Obama's playful intent, the humor. It's incredibly complex.
Trios and layers of inference.
Frighteningly meta, Karpathy called it. And this leads some researchers to the embodiment hypothesis.
The idea that maybe intelligence like ours needs a body, needs to interact with the world.
Exactly. That maybe a disembodied computer, just processing data, can never truly grasp the concepts that arise from physical interaction, from having goals and moving through space. Our intelligence might be fundamentally grounded in our physical being.
Which has huge implications. And brings us to the very real-world challenges and trade-offs of AI today, like self-driving cars.
A perfect example. They're getting good at standard driving conditions, but they struggle immensely with the long-tail problem.
Those rare, unexpected events.
Yeah, the snowman in the road.
Yeah.
Construction zones with confusing signals. Situations where human drivers rely on common sense, improvisation, even guessing other drivers' intentions. That's the hard part.
That intuitive psychology you mentioned earlier. Needed for driving, too.
Absolutely. Predicting pedestrians, understanding ambiguous signals, that requires understanding minds, not just recognizing patterns.
Then there's the whole jobs question. Massive unemployment. Or new kinds of jobs.
It's the billion-dollar question, isn't it? Some jobs will go, automation always does that, but new roles might emerge. AI ethicist, AI trainer, maybe even those moral philosophers for AI, someone suggested, half-jokingly perhaps. It's just very hard to predict the net effect.
And creativity. Can AI truly be creative, like that music program, EMI?
David Cope's EMI, composing in the style of Bach, it produced impressive results. But the source argues it's still human-computer collaboration. The machine generated possibilities based on patterns, but it lacked understanding, taste, judgment. A human still had to curate, to select the truly good pieces.
So we're left with this great AI trade-off, huge potential benefits versus these real risks, errors, bias, hacking, lack of transparency.
That's the core dilemma. How do we harness the good while mitigating the bad? How much trust is warranted, especially when systems lack genuine common sense? Because that common sense, that understanding, it feels like a prerequisite for truly trustworthy moral reasoning, which is something we definitely want in autonomous systems.
All right. Okay, so let's recap. We've traced AI from its, well, wildly optimistic birth through AI winters and springs.
Seen the rise of deep learning, powering impressive but narrow skills like image recognition, game playing.
But also bumped up against its fundamental limits. The brittleness, the bias, the lack of common sense, the vulnerability.
And we came back to Hofstadter's terror. Not the Hollywood fear, but the feel of trivializing what makes human thought special, deep, meaningful.
The consensus seems to be super intelligent, conscious AI.
Yeah.
It's really not just around the corner.
Not on the horizon, no. The real legitimate worries are here and now.
Yeah. The potential for dangerous and unethical uses of algorithms and data. That includes job disruption, misuse of AI, its unreliability, and how easily it can be attacked or manipulated.
Those are the pressing concerns. But on a hopeful note, there is a growing awareness. The source mentions a developing sense of cooperation and common purpose among researchers, companies, policymakers to actually tackle these ethical and safety issues. That's encouraging.
It is. So we'll end with the author's closing thought, a challenge directly for you, the listener. She says, I hope that this book has helped you, as a thinking human, to get a sense of the current state of this burgeoning discipline, including its many unsolved problems, the potential risks and benefits of its technologies, and the scientific and philosophical questions it raises for understanding our own human intelligence.
And then adds a little kicker.
Right. And if any computers are reading this, tell me what it refers to in the previous sentence, and you're welcome to join in the discussion.
Hey, a nice test.
Indeed. That's it for this deep dive. Hopefully you feel a bit more grounded, maybe more curious, and definitely less lost in the complex, fascinating world of AI than perhaps our author was in the Google Maps building.
Factoring can meet the cash needs of manufacturers impacted by rising tariffs. Contact Chris at Versant Funding to learn if your client is a factoring fit.